All right. Hello, everyone. My name is Han. I'm very pleased to present you the research work we do in our group in this ANFF Research Showcase. Here, I'm going to talk about the silicon metal oxide semiconductor, quantum dots qubits, and how they are made using ANFF facilities at the New South Wales node. All right. So the ultimate aim of our research is to build a quantum computer. It is a very ambitious goal, obviously, especially for a quantum research group in a university using the facilities in an academic lab. Honestly speaking, it is unthinkable for us to be able to build a practical quantum computer with millions of qubits out of an academic lab. But everything starts from somewhere, right? So just like the smartphone that you have, which consists of billions of transistors. The beginning of it is actually a single transistor, right, which was invented like back in year 1947. So here at UNSW, we have built the first 2-qubit logic gate in silicon, which is the fundamental building blocks for a future quantum computer. There are a number of approaches to realize a physical qubit, and our group is specialized in working on the quantum dot qubit, which we can initialize, control, and measure an electron spin in a silicon metal oxide semiconductor system. So what motivates us to build a quantum computer? All right, a quantum computer can solve difficult problems with its massive parallel processing power. To illustrate an example, using a classical computer, it is very easy to calculate the multiplication of two numbers. So it can calculate very easily and very quickly. However, to factorize a big number, this 2,183 is not big enough, but to factorize a very, very big number into its prime factors, right, using a classical computer, it is very hard, and it is very slow, and it is extremely computational intensive. And this is actually what RSA encryption algorithm is based on, so that we can transmit our information safe and in a safe and a secure way. With a quantum computer, based on superposition principle and qubits entanglement, these types of problems can be solved exponentially faster. So because of its huge potential, right, there's been a huge amount of effort and increasing amount of investment in quantum technologies worldwide over the past few years, as you can see from the map here. In Australia, the government has invested around 130 million Australian dollars for the development of quantum technologies. In fact, there are 4 quantum-focused ARC Center of Excellence in Australia, namely CQC2T, FLEET, Equus, and Exciton Science. And because of its huge potential in revolutionizing the computing, there's also a growing number of quantum technology startups. Just to give an example, in Sydney, we have Silicon Quantum Computing, SQC, based in University of New South Wales, and we have Q-Control, based in University of Sydney. So besides this startup, we also have big tech companies like Google, Microsoft, IBM, Intel. They are all investing heavily on this quantum computing field. So I think that's enough of a motivation to convince you why this research is important. So in our group, all right, we have made qubit out of an electron spin. So this is the device that we make using ANFF facilities for our research group. So it's a very simple device, and it's very similar to the MOSFET. This is the SEM top view of the device, and below it is the cross-sectional cartoon. So what we have here is the aluminum metal on the top, and then silicon substrate at the bottom. And then in between them, we have a high quality gate oxide as the insulation layer. So in the silicon, we have implanted or diffused phosphorus donors to define the source and drain contact. And when we apply positive voltage on the top gate, it accumulates a layer of electron to form the channel. And once you apply this positive voltage, the channel is formed, and then this turns on the MOSFET. So what we do in our research is we introduce these two barrier gates here to trap electrons in this region here, and which we call it an island. All right. And as I said before, we need to confine a single electron. All right. And that will be our qubit. So what we need to do here is to reduce the top gate voltage to slowly deplete the electrons one by one from the from the dot, from the island. But in this particular architecture, as we reduce the top gate voltage to deplete the electrons, we also cut off the electron channel, so that, and this prevents us from determining the number of electrons in the island. So 2 years later, which is in 2009, we tried to modify the structures, redesign it. But basically what we did is to split the top gate and then into 3 different gates, which you can see here, L1, L2, which forms the electron channel. And then we have this independent plunger gate here to control the number of electrons in the dot. And with this design, we can confirm that we are able to confine a single electron in this island. And because of the fewer electrons, we call this a quantum dot. So, and because of this paves the way of our quantum computing research using silicon technology. So let me go through this fabrication process of silicon double quantum dot with you, all using ANFF New South Wales facilities. So first of all, we have this purified silicon. And what we do is we diffuse phosphorus into the silicon to form the N+ contacts. And then we grow a high quality gate oxide of 8 nanometers via the ultra dry thermal oxidation process. So what we do next is to use the electron beam lithography to define the barrier gates. And we deposit the barrier gates with aluminum using thermal evaporation process. And then we thermally oxidize the aluminum to form the aluminum oxide. The same process is done using the same lithography process to define the lead gates, which is L1 and L2, and then the third layer of EBL gates, which is P1 and P2. So here from this cartoon, you can see that a double quantum dot is formed in this particular device. And before we do any measurements on this quantum dot qubit device, we perform a final forming gas anneal at 400 degrees Celsius to improve the quality of the gate oxide. And you can see these happy faces hiding behind the mask is when we managed to successfully fabricate a batch of working devices. And what we do next is we need to bond and package the device so that we can measure in dilution refrigerators. So this is the silicon chip where we use aluminum wedge bonder to bond it to the PCB in a copper enclosure, and then we mount it at the cold fingers of the dilution fridge and measure it at millikelvin temperatures. So I just want to highlight here in this particular slide to kind of highlight the similarity between our ANFF devices and the MOSFET device that is made by Intel, all right, back in 2005. So there is this polysilicon gate on top, and then there's a layer of 1.2 nanometers of gate oxide, and then underneath is a silicon. Our device is very similar, right? It's 3 layers, metal, oxide, and semiconductor. So by leveraging this multi-trillion-dollar SiMOS advanced manufacturing industry, we do believe that 1 million plus physical qubit processor is achievable in the foreseeable future. And then I just want to share with you some of our recent results. So we realized the first 2 qubit logic gate in silicon. This is a device made in ANFF. there's this 2 electron, 2 qubit here, and we can count the numbers of electrons in the 2 quantum dots by using this silicon electron transistor, which is placed nearby to the quantum dots. We can apply microwave signal to this aluminum antenna on chip, and then to rotate the electron spin, which is shown as this Rabi oscillation, as shown in this panel D. And last year, we managed to demonstrate the operation of silicon qubits at a higher temperature, which is 1.5 Kelvin. And this is an important result because it significantly reduced the operating costs, and it enhanced the prospect of scaling up the number of qubits in silicon. And it is also worth mentioning that Intel is also busy making silicon qubits using their FinFET technology in their foundry. And this is their TEM image of the device they make. You can see that the gate profile is very uniform. And also, they also reported that their oxide quality is top-notch. So this silicon quantum computing research is just getting more and more exciting. And this is my last slide. I just want to acknowledge all the fantastic work by my co-workers in Zurek Research Group. This is quite a big family led by Professor Andrew Zurek. And not forgetting, I would like to express my appreciation to all the ANFF engineers who work tirelessly in the clean room to maintain the equipment so that we can make working devices. All right, thank you for your attention.
Thank you very much for your talk. And now looking on the app, I see that there are no questions. Anything in the audience? But I do have a question for you.
Sure.
Standard algorithms that the computers are using right now rely on 1 and 0. And they're very efficient in doing so. Quantum computers are different. It's 1 and 0 and something in between. Is there an easy way, but it must be an easy, simple way to explain what is the underlying reasons that they are so fast, so much faster? What
I'm not sure whether I have an easy way to explain that, but it is making use, like in the classical bit, it's just 1 and 0, right? But in a quantum bit, it's not just 1 and 0. You also have superposition of these 2 quantum states. And because of that, in addition to these quantum qubits entanglement, they can actually do the computational processing in a parallel way to do this quantum computation. So what we need to do is to think of it like a quantum gate. It's similar to what we have in the classical computer, where we have like a CNOT gate, all right? So that we can do addition, subtraction using all these CNOT gates. In quantum computing world, we also managed to use these qubits to form a quantum CNOT gate that will help in our computing the calculations.
Thank you for your answer.